Okay, everyone. So I wanted to review this worksheet with you guys. Um, so we will start off with the beginning here, and I think we did pretty well with this as far as understanding the purpose of this experiment. I guess I just wanted to highlight density again. So density is a measurement to describe this mass per volume. So I've written the word compactness, which may not be a word that you know. Compactness. And we also looked at the density of a material, so such as a metal, will be the same even if the shape is different. Okay, so I think some of you were a little confused because you were thinking of things like an aluminum can and then like crushing the can, how the volume changes. But you have to understand, when I'm talking about density in this case, I'm talking about solid objects. And I guess I should have clarified. Okay, something like an aluminum can has air inside of it. Okay, but all of these are completely solid. There is no air within them. Okay, so they're looking at these three separate objects. They're different shapes, and they think that they're this metal called ethium. And ethium's density is 320. So Jenny and John want to confirm that these objects are ethium, and by doing so, they will need to find the density. So they will need to find both the mass and the volume. Okay, so the question that they're trying to solve is, so what is the problem in the experiment? So Jenny and John want to confirm and honestly, a lot of times the purpose of the lab will be kind of buried into one of the background paragraphs, right? Usually the person's going to tell you what the purpose is. Want to confirm. Okay. All right, so we know that Jenny and John have to take measurements for each shape. And so what I wanted to ask you guys here is, what's different about, they're basically doing the same experiment 3 times. So what's different is the shape. Okay, so the independent variable, and this is kind of maybe an unusual case, right, because we haven't really learned physics yet. But the independent variable in here is what is changing, and that is the shape. So we have 3 objects. So what's different each time they're taking measurements is the shape. So the shape okay, and then normally we will only have 1 dependent, but this time we have 2. Okay, so, and I'll in the beginning I will remind you that is what they're measuring. Okay, it's not density or volume, because you have to calculate those. Okay, so instead what they have to do before they can calculate the volume is they have to measure the dimensions of the object. So this is like the length, the width, and the height of each object, and they're going to be using the meter stick for that, and the mass. Okay, so those are the two things that they are measuring. And there's a few controls that we could use, but I would say two of the easiest ones that we could use is same length measuring tool, and which is the meter stick. And the reason why I kind of say this is since they're using the same tool, that tells us that all of their measurements are going to be to the same precision, right? A meter stick usually measures to the nearest centimeter with precision, so it doesn't measure to like the nearest micrometer or anything. And same mass measuring tool. So basically the mass scale. Okay. Okay, everyone. So on the back page we have the hypothesis, and I kind of wanted to go over this and also kind of apologize a little bit for a little bit of oversight here. So with the if-the part, we're going to insert what we said was our independent variable, and that was if the object and the shape of the object changes. Okay, so since there's three separate objects, we know that the mass and the dimensions that they're measuring are going to be different. And I guess the mistake that I made here is, in this case, the word because doesn't make a lot of sense because we want to tie this back into the purpose of the experiment, right? The question, related back to the question they're trying to solve. And that's really about the density if the material is the same. So usually the word because works very, very well. Like I said, this is kind of an unusual experiment that we will kind of practice in class. So I'm choosing the word however, and then I'm relating it back to the density. So if the object's shape changes, then the mass and dimensions of the objects will change. However, the density of each object will be the same because each object is the same material. So this part here, this is like my prediction part. Like my prediction is right here. And I can't fit that in there, but prediction. Okay. Also, you know how you guys write a paper and you don't realize mistakes until maybe a teacher or a friend tells you? It happens to teachers too. So William noticed this. This was oversight on my part. I was thinking about the sphere's radius, not about their measurement. Because when they're measuring, they're going to be measuring the diameter, right? So all of these values should be doubled. So the radius is 0.25. It shouldn't change the calculations. I just made a mistake there. I'm sorry. So if they are measuring the diameter of the sphere, that means the radius will be 1/2 of 0.5, so 0.25. And for the volume, we're going to do 4/3, which is 1.33, times 0.25 cubed. So maybe I'll write this below. And this is on the front page of the sheet. 4/3. And we get a very small number, 0.021. So sorry, I forgot to include pi. So after you multiply by pi, it's 0.065. Okay. So if I know the mass and I know the volume, the density is going to be that 20.542 number divided by 0.065 meters cubed. That gets us 316 kilograms meter cubed. Okay, luckily to find the volume of the cube, it's just the length times the width times the height. So it's just going to be 0.3 cubed, which gives us 0.027. And the density will be this mass divided by this. So 289 divided by 0.02. Get 307. Oops. And for the pyramid, we take the length times the width times the height, and then we divide it by 3. So remember, this is on the front page of the sheet. And that comes out to be a very small number. Okay, the volume of the pyramid is very small in comparison. Okay, so since it has a small volume, the mass will be small, and the density that we calculate is 338. Okay. All right. So, our first analysis question: if the objects are the same material, they will have the same density. Does this seem to be true? Okay, so there's definitely some difference here, but they're relatively close. So the densities are relatively close. To that 320 value, kilograms meter cubed value. Are each of them the same? No. Some are low, some are high. Okay, and we'll talk about the reason for that later. So even though I believe this to be true, this is fairly low precision. So the average here is going to be 316 plus 307 plus 338. Oh my gosh. Divide by 3. And we get a very nice looking number of 320.33 repeating kilograms meter cubed. Okay, so what is the percent error? Well, I can tell you this is going to be a very small percent error. So our measured value, 320.33 minus 320 divided by 320 times 100. we get an extremely small number of 0.1%. That is extremely small. So are the results accurate? Yes, they are very accurate. Okay, remember, if it's less than 5%, it is considered very accurate. Okay. So for number 4, we can, I guess I meant to say diameter here, but the point of this still works. So do these measurements seem to be precise to you? I'm going to say no. Okay, so remember in the data table it showed the average measurement, which I had as 0.25. So if we add all 3 of these up and divide those by 3, we will get an average of 0.25. But look how different they are. Okay, they vary by plus or minus 0.06, and our average is only 0.25, so that's a very big difference. That's basically a 25% like precision error. Okay, which like you wouldn't have to write, but you would just explain that varies a lot. Okay. Okay, so let's look at the last one. So the densities are not exact. Okay, random error affects precision. This is usually due to human error. And systematic error is usually because of a calibration error or a major fundamental reason, fundamental incorrect thing with the experiment. So this is definitely due to random error. And the reason is we have high accuracy and low precision. So if we have high accuracy, it's not systematic. And the biggest error that we can see is poor measurement. So human error with probably the meter stick. Okay, so I think this is good to look at before the test. You'll have to kind of use these skills on the test, even though the scenario will be easier. Okay, I told you on the test it will be similar to the Smoots measurement, which was the lab that we did in class. Okay. Another thing that I meant to kind of look at for the test is if I were to give you something like this, could you give me a trend line? Or a line of best fit? Okay, so this one happens to be going down, but this is supposed to be, this is actually very hard to do on this iPad. This should be a line that best represents these points. Let's see if I can do this here. Okay, so it should, if you can see this, it should be right here. Right, it kind of seems to best represent these. Yeah, so my line of best fit would look about like that. Okay, on your test, do not, please, do not do this. Okay, don't do that. That'll make me very, very sad. And finally, if I give you something like, I'm just mentioning things I forgot to mention in class. Convert metric units. So if I give you something like 20 milligrams, and I tell you to convert it I'll say to grams. Okay, I want you to practice this with dimensional analysis, meaning I know a lot of you guys can do this in your head, but that doesn't tell me anything. And next unit, we're going to have harder conversions. So what you want to do here with this dimensional analysis is what I call 2 over from. Okay, so what is the unit I'm going to? I want to go to grams. What is the unit I'm coming from? I'm coming from milligrams. Okay, so right away, let's go ahead and put those quantities here. And what you'll see is that if we have milligrams in the numerator and milligrams in the denominator of our fraction, they will cancel out. And the last thing that we need is a number value to represent how many milligrams are in a gram. Okay, so I know that 1 gram is equal to 1,000 milligrams. Okay, so I'll do that. Okay, that's how I want you to write it in order to get our correct value. Okay, so it's 0.02 grams. Okay, so study this stuff, please. And I'll see you later. Bye-bye.